So, just one second, let me get the screen. Okay, so on behalf of the Indian Association of Structural Engineers, we are, and in the capacity of the chairman of the events committee and the vice president North of the association, I would like to welcome you all to this great event of cable stayed bridges, which is, convened, or the main author of which is Professor Holger Svensson. Or so, and he is also very kindly graced this occasion that he will be giving us a little introduction at the same time. So today is a special, he is come in person along with his assistant, and they will be there at the at the panel discussion at the end of this today's lecture. So let me, with that, start with a little introduction about the panelists. So first of all, I'd like to introduce Mr. I.K. Pandey, who is the DG Road Development and Special Secretary, Ministry of Road Transport and Highways. He is also presently the chairman of ING IABSE and is involved in disseminating knowledge in the field of bridge engineering through workshops and seminars across the country. Then we have our own, very own luminary, Professor Mahesh Tandon. He is the past president of IAStructE and managing director, Tandon Consultants Private Limited. He is an international expert in the field of structural engineering and convener of subcommittees of B9 IRT and with responsibility of drafting cable stayed bridge code in India. G. Sharan, who is a former DG RD and SS, Ministry of Road Transport and Highways, and convener of the 9 Committee of IRC, responsible for special structures, including cable stayed bridges. Then we have Mr. Mahabir Singh, who is a member, Technical National Highway Authority of India. He possesses vast experience and proficiency in the field of planning, design and execution of roads and highway projects. Excuse me. Then we have Mr. Thoraf Kastner, who is he's a graduate. He's a research assistant at the chair for steel construction at the Technische Universität Dresden, with the research focus on higher strength steels, welded joints, old steel structures, and hydraulic structures. Topic of this dissertation is on the influence of manufacturing parameters on the mechanical properties and welded joints of higher strength steels, and is almost a PhD pretty soon. So hopefully in the future we have another seminar and we'll call him Dr. Thoraf. Then we have finally our very own Mr. Alok Bhumek, who is the managing director and of B&S Engineering Consulting Private Limited, and our president, of course, and a bridge expert and a leading consultant. So currently, of course, he's the president and an active GC member of CEAI. He has accreditation of international PE in India. Thank you very much. So now I'd like to invite Mr. Alok Bhumek to take over the proceedings and take it from here. And we welcome again you all to this very exciting cable stayed bridges seminar, which I hope will really go along in capacity building in this area, is what we desperately need in our expanding and promising economy, in which we would like to follow the Prime Minister's Atmanirbhar Abhiyan. Thank you very much.
Good morning, good afternoon, and good evening to you, wherever you are, ladies and gentlemen. I'm addressing this to people from Germany to Malaysia. Welcome to this inaugural session for this online lecture series on cable-stayed bridges, which is being organized by our association, that is Indian Association of Structural Engineers. Friends, today is a very special day for all of us. As you all know, many of you know that in India, we celebrate 5th September as the Teachers' Day. Today is the birth anniversary of one of the most distinguished scholars of 20th century in India, that is our former President of India, Dr. Sarvapalli Radhakrishnan. He was honored with knighthood way back in 1931. He was honored with the highest civilian award in India, that is Bharat Ratna, in 1954. He was nominated for Nobel Peace Prize for 16 times and for Nobel Prize for Literature 11 times in his career. No other day or occasion could have been better than today to welcome Professor Holger Svensson, the presenter of this lecture series and the author of a very popular book on cable-stayed bridges. It's a very special moment for all of us, and I, on behalf of all the participants and all the members of Indian Association of Structural Engineers, heartily welcome and salute Professor Svensson for agreeing to spend a day with us and sharing his series of lectures on cable-stayed bridges with us. Sir, I can tell you that from today onwards, you have added 300 students in your register. I can say that, in fact, you have added a students' chapter in India. I also take this opportunity to thank Dr. Or would-be Dr. Tharaf Kaisner, who has joined us from Dresden University, who is working under Professor Svensson, and he has been interacting with me for this, coordinating for this lecture. Friends, this lecture series will be moderated by our own Dr. Harshavardhan Subbarao, one of the eminent structural engineer in the country, who is, you can say, India's brand ambassador in IAStructE or FIB and many other international forums. I have the pleasant duty to introduce him to all. But before I introduce the moderator, I would like to thank all the participants for this course. We are overwhelmed by the response that we have received. Let me tell you that we have more than 325 participants who have registered for this course, and we are still counting. It shows the strength of online course, and it shows the topic that we have chosen, which is a pretty demanding topic for India. Several cable-stayed bridges are in the pipeline or under construction, and therefore this topic has generated so much of interest. Let me also tell you that in the past, in the best of circumstances, in IAStructE, we could not gather so many participants for one event. So this is indeed a very satisfying, and I must say that it is one of the very few positive impact of COVID-19 that we are witnessing. I now have the privilege to introduce our moderator, Dr. Harshavardhan Subbarao, a close friend of mine for last 2 decades. He is the chairman and managing director of a leading firm, namely Construma Consultancy. He holds a PhD from Imperial College London. He is an active governing council member of IAStructE and is vice president of the IAStructE Zurich. He is also member of technical committee of Zurich IAStructE and chair of its bulletin edit board. He is member of FIB Commission on Durability and Service Life Design, member of Highway Research Board in India, and serves on several committees of IRC, BIS, and various international national bodies. He has more than 30 years of experience and a number of technical papers to his credit. Before I hand over to Dr. Subbarao for moderating the event, I have another pleasant task to talk a little bit about our own association, that is IAStructE. IAStructE is a national professional body of structural engineers established with the objective to cater for the overall professional needs of structural engineers in India. It was conceptualized and constituted in the year 2002 by few eminent structural engineers, and our founder member is Mr. Mahendra Raj. At the age of 96, he is still a very active member of our association, and he is a torch bearer, and he is showing us the path. A prominent thrust area of Indian Association of Structural Engineers is to ensure that its members have the requisite technical knowledge and experience updated on a continuous basis. We are organizing various events such as these continuous professional development courses, refresher courses, workshops, seminars, public lectures. We used to organize prior to this COVID monthly technical lectures, which has stopped now, and it has been converted into webinars. We also organize technical visits to various project sites. IAStructE also prepares technical guidelines, commentary to various codes and explanatory handbooks for the benefit of practicing structural engineers. By joining the association, members will be in close proximity with many engineering specialists and committed experts having a vision of sustainable future for structural engineers. With this brief, I would like Dr. Harshavardhan Subbarao to take over from me and start the proceedings. Dr. Subbarao, please.
Thank you. Wonderful to meet again on this platform. Those of whom I met before and those who are new to IAStructE's event, welcome all. We are delighted that you've joined us. Your response has simply been overwhelming, and we are delighted that we could share all this knowledge with you over a series of lectures that will ensue from coming Wednesday onwards. Today we have with us Professor Holger Svensson, who is an internationally renowned expert. He has headed a firm which is legendary in the domain of bridge engineering called Leonard and Andra and Partners. It's a legendary bridge firm, and he has headed that. So you can imagine the kind of knowledge and the kind of wisdom that you will be getting in this course from one of the best teachers in this subject. So Professor Holger Svensson was born in Hamburg in 1945. In 1969, he'd finished his diploma at Stuttgart, and he was there as a lecturer for some time. And from 2012, he has been a professor of cable-stayed bridges. Note, professor of cable-stayed bridges at University of Dresden, Germany. His career goes on as 70 to 71. He was with a contractor in South Africa and Botswana. 72 to 2009, so many years. He was with Leonard Andra and Partners, consulting and designing on various major cable-stayed bridges. He became their executive director for a period of nearly 10 years thereafter. And he was a speaker of the executive board at that time and became finally the chairman of the board. Since 2010, he's been an independent consulting engineer, and he says he's now retired, but I don't think that's likely. And it's not as if that we're going to leave him in that condition, if that is so. We will be troubling him again and again for his knowledge, which I'm sure as a teacher, he would share with all of us. Holger Svensson has extensive experience in design, construction, engineering, and on-site supervision of cable-stayed and other long-span bridges all over the world. In Germany, he was involved in the checking of the Korscher Valley Bridge and detailed design of the cable-stayed Flair Bridge. In the US, he was involved with the Pasco-Kenwick Bridge in concrete, East Huntingdon Bridge in concrete, Sunshine Skyway as the composite alternative, Burlington as a composite cable stay, the Houston Ship Channel crossing at Baytown in composite. So you can see he has composite and concrete, both in his, and steel, all in his domain of knowledge and experience. In Norway, he was in charge of the design of the Helgeland Bridge, and in Scotland, he advised on the design of the Leven River Bridge, both concrete cable stays. In Sweden, he was checking engineer for Hagakosten Suspension Bridge, main span of 1.2 kilometers, and the Sunningsund Bridge and Alv composite cable stayed bridges. In Australia, he advised on the design of cable stayed Gelb Island Bridge, concrete bridge in Sydney, and on the Mai Tuan Bridge in Vietnam for Australian aid, that's AusAid. For the Asian Development Bank, he has reviewed the design and construction of record-breaking cable-stayed Yangpu Bridge with a main span of 602 meters in Shanghai. In Hong Kong, he's advised on the design and construction of Kap Shui Mun Bridge to Lantau Airport. He was also responsible for the design of several major bridges and arch bridges in Germany and elsewhere. I cannot tell you how fortunate you are to be, for him to be gracing this inaugural event of ours with his personal experiences, and he will be talking to us on that in a few moments. But friends, before I invite Professor Svensson to speak, may I also take this opportunity to thank his student, Thoralf Kastner. He has already been introduced, but he works with Professor Svensson as a student, and we wish him all the best in getting his PhD. I had done my PhD at Imperial College in the same steel structures that he's doing, and I know how difficult it is to earn one. So I wish him all the best. And on that note, I would like to share with you a few things before we start. One is, please keep for the bandwidth issue, please keep your videos always off and your microphone on off. Keep them switched off and muted at all times, and we will then interact with you in the question answer session. Please note that there's a Q&A box. In the Q&A box, I would request all participants to put their questions only in the Q&A box and not in the chat box. The chat box will not, the questions arising in the chat box will not be answered or taken up in this session and in ensuing sessions. So friends, we have a series of lectures to look forward to improve our knowledge, and to come to the frontiers of something that we hold as magnificent in our heart, a cable-stayed bridge. Any cable-stayed bridge evokes a deep cultural sense of well-being in us. Any cable-stayed bridge gives us a sense of grace, aesthetics, and pride as engineers. So what better topic to choose than in the coming days of the engineering day that we will have, and on today, the Teachers' Day, a topic which inspires us all, which will inspire with its form, with its grace, with its beauty and its functionality, something which represents probably the acme of structural engineering to many of us, and entirely to the bridge and to the entire bridge community. So we welcome you, Professor, and we thank you again for allowing us this kind permission of yours to host this series of your talks and your teachings. And I assure you, as Alok said, you have not only 300 students in your, to add to your list of students who you've taught over all these years as a master teacher, as a guru, what we would call a guru in our Indian words, you're a guru, and we welcome you to share your knowledge and your experience with all of us. Thank you, sir, and I will hand over back to the organizers to lead the event. Professor, you can actually go on air now. And you can take about an hour, no problem. Over to you, sir.
Well, good afternoon to all of you, and thank you very much for the kind words you found to me. I'm also very impressed that we have about 300 students from not only India, but various countries around India. That makes me proud to talk to you. Now, I just want to go into not so much on the technical details. They will be part in the lectures to come, but I thought it may be interesting to listen to some personal experiences I had in the design of cable-stayed and some other bridges. Transportieren? Just a moment, I have to consult Mr. Kestner.
No worries.
Okay, so now this gives a brief overlook of some general and German bridges, and then I talk about cable-stayed bridges abroad, checking, working on codes, some ongoing projects, and how I see the future developments. That's some problems here. Okay, here we go. Now, my sponsor and teacher over 30 years was Professor Leonhardt. At the end of high school, I already had the wish to become a bridge engineer, if possible, on major bridges and all over the world. And so I studied in Stuttgart University under Professor Leonhard. Hold it, that's too fast. Okay. At the end of the study, I went to Professor Leonhard, who I had somehow known as a speaker of my class, and asked him for a job abroad. And he said, well, I can send you to South Africa. There was a contractor who had our license in post-tensioning systems. And so I went for 2 years to South Africa. 1 year was planned in the office, in the design office of the contractor, and 1 year on site. So the 1 year I spent in Johannesburg, in the design office, and worked on everything which you can imagine, from buildings and small bridges and so on. I had everything. It was a very good way to get involved in things. Then after a year, I was to go on site, and Greniger proposed to me that I go to Botswana, a black state north of South Africa, where together with Costain London, Greniger was building a copper nickel mine. That means all processing above ground. And we went, and it was a place right in the middle of nowhere. We had first some tents. You can see me here in the safari suit, which was de rigueur in South Africa. And we had tents, and we looked for water, and we crushed our own stones. And it was quite an involved thing. For free time, we played soccer a little bit, but mainly I played then tennis. And we built our tennis court after lots of tries from termite hills, which were the right thing to use as material for a tennis court. So then after a year, it was time to come home. I mean, when we went together, a bottle of whiskey ahead was not unusual and things like that. So after a year, it was time to go back to Germany. And I went to Stuttgart to Leonhard's office and became a design engineer. And we had some interesting major bridges to build, because that was the time when the German freeway system was expanded, and the biggest bridges, we were, I say, lucky enough, were given to our company. Now, the first I worked on was the cable stayed alternate for a Kocher Valley Bridge, not close to Stuttgart, for a freeway. And the point was that the geologist stated you could not put foundations into the slopes because they are creeping. There's a bad soils condition in there, and with water comes to it, they creep. And so with long side spans, Leonhard had the idea, and he grabbed it and said, well, we'll build a cable stayed bridge with 600-meter main span. That would have been world record. He liked that very much, but the geologist retired. And his successor said, well, it's not as bad as that, and you can build with some conditions in there. And so the bridge which was then built was a continuous girder 185 meters above ground. That was the highest bridge in Europe for a long time. The Millau is higher, but that only was some years ago. And it has this parabolic sides there, and it's quite good. And after the end, the foundation problem was solved by building large wells at the foundation, and to put the towers into the wells with about 1 meter distance to the side. So there was ample space, should the slope ever creep, to move without touching the foundations and touching the piers. The next bridge, which was came up down to Lake Constance, was a bridge across the Neckar Valley. Now, there was the same problem, was same soils conditions. It was 120 meter high and large slopes which tend to creep. And in this case, the chief geologist did not retire, and he remained in charge. And we had lots of discussions how to bridge those 200, about 50 meter side spans. I mean, you know, a side span is about structurally 25% bigger than a main span. And it was finally solved by using air struts. We see it here, and we see it here. So we stayed from underneath the side spans, which is very effective for permanent loads. It acts like an additional pier. Live loads, of course, they have the big span, but it's possible. So that's how we solved that problem. And I think it is the only bridge, at least I know of a major bridge, with a side span stayed from underneath with an air strut. After we had more or less finished the design, Leonhard came one morning, I still remember that, to the office, and he said, that's a beautiful river valley there, the Neckar Valley. We must keep that open. So he then said, we want to use single piers for the two center spans. Well, could be done, but we had completed our design more or less. We had some fixed dates, and so we were not too happy by that change. But in the end, it showed up, and the bridge was you could see through, was very nice. Then came, after others, the Flehe Bridge, which was 320 meter with one tower, so it's quite a big bridge. And we were in charge of the detailed design. Let's say it is what I call a composite bridge. We have a steel main span and a concrete side span as a cant ledge, so to say. And we had the detailed design of this backstay part with where the main bridge was anchored, and it was built in free cantilevering quite a bit, and the approaches where I was also working on were built by sliding formwork span-wise, 60 meters, 60 meters, 60 meters. And it's story to say that although it has by God been surveyed in all details, when we arrived at the tower, it was found that the tower legs were positioned 25 centimeters out of bounds, out of center. So nobody could understand later on why, for years, it has had surveyed, but the 25 centimeters were there, and I think it was to the river. So our last element was not 60 meters, but 60.25 meters. Some more bridges. I just get the German bridges in front, which are interesting because then later I come to the cable stayed. This was after the German reunification. The Autobahnen, or the freeways in East Germany, had to be widened. They were all very shallow. And so we then had to widen this bridge. And you see here the old piers, and it was planned to take them down and build new piers and everything new. But Leonhard protested against. He was in charge in the 1930s when he was with the Federal Ministry of Building. He was in charge of building those piers and had some discussions. And the piers itself were not covered by codes because the concrete was just tempered, but not the usual equipment wasn't used. And so, but he succeeded. Nobody else could have done it, that they were still okay, and so they were kept in place. But then the new bridge was quite wide, and the new bridge was first, the new bridge was here on auxiliary piers. You see here these auxiliary piers. Then the roadway on traffic, this was broken down, and the whole thing was then shifted to the side onto the old piers, which could very well take the full load. Another bridge in East Germany was the bridge across the Warnow. And I said, okay, I want that job and we'll get it. And we gave in a low bid. And the reason was that I myself come from Hamburg, North Germany, and actually Gestacht, a small suburb of Hamburg. And then was for, well, all the study and that for many years in Stuttgart. And I spoke what we call Plattdeutsch, the North German dialect, which I didn't speak for many years, and I wanted to speak it again. And so that was the reason why we got that job. And actually we had then a geologist who also spoke Plattdeutsch. And I went to all the site meetings, and we had a good time speaking my native North German dialect. A little smiling thing was we had to widen, after preliminary design, the span by 2 meters on each side to prevent the beavers running against the towers when they pass along. I mean, that's absurd, but the Greens had these ideas and it was done. Later on, I was involved in the design of the intersection of the Neukölln highway in Berlin, and it was planned as one of the few without merging lanes. So all connections had to be direct, and you see that And that was in 4 levels, with 1 level underground and 3 levels above ground. Close to that intersection was a crossing of a canal, and it had to be an arch bridge that was relatively clear. But we made something new. Instead of having 2 arches side by side, meaning 4 arches, we had the center arch concentrated in one with the same outside dimensions. Naturally, the plate size was about double. And we also had a continuous roadway over that, which was not accepted in general by the Federal Highway Administration because of exchange and so on. But we showed with that, in that respect, you could take off the wearing surface and put on a new with what traffic on one side and the vibrations were and so on. So that was something new, but we succeeded to get that through. Now, those were some major bridges I was involved in Germany. And then I want to go onward to cable-stayed bridges abroad. The one bridge which is important there is, and for myself, for my development, is the Pasco-Kennewick Intercity Bridge. It's in the state of Washington, top left of the map. Not Washington, D.C., but the state of Washington. And we, Arvid Grant, a small engineering office, approached Leonhard about some advice. He had a job. And we then went to it, and Leonhard came up with, as one alternate, with the cable-stayed bridge. And at that time, there were no cable-stayed, virtually no cable-stayed bridges in the US. And the chief of Federal Highway Administration wanted to build a cable-stayed bridge in the US. He had already written a book about that and so on. And this was the reason why this design was accepted and paid for 85% by Federal Highway. And so we started with a 300-meter world record span. That was during the beginning. Later on, the French started later, but they were ready before we with 320 meters, so we didn't get the world record, but initially, at least we had it. And this was planned as done in Germany, cast in place, free cantilever, but it became quickly clear that American contractors were not prepared to have free cantilevers, 150 meter each side, in cast in place. No way. And so we said, okay, then we'll make it precast. And that forced the precast solution. And we had we see here the precast elements are lifted up. And I was coming to the US. We had preliminary design made in Stuttgart in the 74, 75. And then I went to the US in 76 to see how the detailed design developed and so on, which was task of the other office, the main consultant. And I found out very quickly that there was nothing you could use. And I spoke to Leonhard on the phone. At that time, there was no internet, no we had a you wrote letters, more or less, or you telephoned. There was not much connection. And I told Leonhard that that's not going to go. I have to remain here. And so then I remained in the US alone, and I was in a way a beginner. And it was quite fortuitous from Leonhard to let me do that job. And I found my wife, who had, we had a 2-month-old son, and she came by plane, and I had meanwhile rented a completely furnished house and borrowed baby things from our office. And so my wife could settle down. The design was not so simple. I mean, it was a record span, but this 2 times 72 stake cables, and as well statically indeterminate, was difficult at that time. 1976, there was not much of a computer at that time, and the only program available was Strudel. You may or may not know the old truss program. And so we had to go to McDonnell Douglas in St. Louis and rent from them. They had the biggest computers available in the US. Time at night, 1 or 2 hours, to run the different erection systems. The permanent load system we had to do by hand, because the matrix doesn't have a governing diagonal as normally is the case, and the result was numerically unstable. So we got 3 times calculation and got 3 times different results. So we did that by hand. And also for the construction systems, one after another, one has to add up the action forces, which are the result of this system, to the one before. And that could not be done with changing systems. So we had to do that by hand, and we had large sheets with people scribbling in and so on. But in the end, it came out all right. The first check you do with a construction calculation, doing it backwards as was used at that time, that all action forces, moments, shear, normal force, of those elements which have been dismantled, which are not there, are 0, naturally. And it was the case. So my colleagues, US colleagues who worked on that, were quite amazed that after that real maximum amount of calculation, we really came out with 0. And the proof of the cake was that at the end of construction, when all cables are first in, you check the cable force through one after another. And we did not have to recheck any cable, which is, for a construction engineer, a high mark. Normally you have to stress a little bit of things on it. But we didn't have to re-stress. And so I'm quite proud to say the first I did went perfectly. And the construction itself was also, Peter Kiewit, sons did it very good. Well, after some time, then there was another cable-stayed bridge across the Ohio at East Huntington. And that was in a way even bigger, because we had 250 meters with one tower only. The main problem was that initially the design had been given to T.Y. Lin as a steel design. But then during the design phase, Federal Highway changed its policy because they wanted alternate designs. Now, American contractors are not prepared to offer alternate designs. Insurance, all sorts of things, and they don't have an own office. And so another consultant was then given the task to design with another material, in this case, in concrete, which is now standard procedure since that time. But in this case, the foundations had already been built ahead, and they were made for the steel bridge. And now the concrete bridge we designed was, I'm afraid, a little bit heavier. And so we had to squeeze our concrete bridge, the design, onto the foundations, and we used, for that, we used another cross-section with a steel cross-girder. A little bit steel was permitted. We used high-strength concrete, unheard of in the United States. And so it was possible. Both alternates were tendered, and our one was quite a high percentage. So then, after some time, there came up the Sunshine Skyway Bridge was hit by a ship in a storm, and the main pier was broken down, and the whole bridge came down. Now that is a major bridge, and therefore a replacement bridge had to be designed and built in a very short time. And tenders were asked, and we were shortlisted. We means with Greiner Engineering as main consultants, and we as sub-consultants. Abroad, we always work for a local main consultant, of course. And the other, the concrete, this was a composite called steel alternate, and Jean Muller, French, well-known French engineer, had the concrete alternate. And so we could do this composite alternate only in the US. We had not been able to design it in Germany, because the German codes still had stress determination under service conditions. Later on, it was changed that you take that under ultimate conditions only, but at that time, it was not possible to make such a design in Germany, and you can't very well post-tension longitudinally in the middle part composite cross sections, because the compression you put into the roadway deck in the concrete creeps away partly into the steel. And so less in the concrete where you want it, and more in the steel where you don't like it. These were the considerations we had, and it was all fine, but we lost in competitive bidding, concrete against steel, in a small margin because of some foundations and approach bridges. Well, we lost it. Next one came a smaller bridge across the Mississippi. The Burlington Bridge, which we did together with Sverdrup Corporation. And in that case, both alternates were given to our design group, both. And now there happened something which I think is normal. We fell in love with one design, and that was really squeezed. And we were not so happy with the other design, the concrete design. And so the composite design won. Then in the early 80s, there was a problem of ship impact to be solved. Our office had built 2 bridges in Argentina across the Paraná, the Zárate-Brasilago bridges, the first major cable-stayed bridges for railway traffic. And after those bridges were all completed and done, suddenly the government had the idea it should be protected against ship collision. The Paraná is a major river, and Buenos Aires is close to the sea, so there were really major ships coming in. And my friend Rainer Saul had designed it, and he said, well, couldn't you look into that? And I looked into the design for ship impact, and there was nothing. Nowhere in the world were things to do. And the first one wants to know is, what is the force a bow acts onto a rigid wall? What are the forces? Well, there was nothing, as I say. But I found out that it so happened in my old hometown, Gestacht, was investigated for the atomic power ship Otto Hahn, the collision. And tests were made, and those tests were recorded and so on. And so I could then look into that, and with some, well, not so much detailed, I came out and said, okay, the force P, which comes from a rigid hit of a ship, is not so much, very little actually, dependent on the speed of the ship. It's the size of the ship. It's the speed gives more how long the crushed area is, but the force itself, and I came up with this formula, which is meanwhile in more or less all the codes in some way, and I said, okay, it's a square root of deadweight tonnage for ship size, plus minus 50%. I thought that's the best one can do. This plus minus 50% depends on the construction of the bow. If it's a Navy ship, it has a very hard bow, so it may be plus 50%. If it's an oil tanker, it's little, so it's minus 50%. Meanwhile, that has been reduced to 0.1, and without variation in the codes. It may be too difficult, but that is the formula which is used worldwide. We then had, for the Sunshine Skyway Bridge, where we didn't win the design, we had the job together with Greiner to design protection against ship collision. And we came up with such a dolphin, as we call it. It's a circular concrete and steel concrete part with timber fenders around, and a small ship crushes the timber fenders and can be replaced. And a real big ship turns over the dolphin, but it can be calculated how big that ship can be or how big the dolphin has to be. And so that is a standard solution these days. So this was the actually built Sunshine Skyway Bridge, and we had dolphins here along the side spans, because the side spans are as endangered as the main piers, because one of the main reasons is that the at the helm is drunk, and then he can go left and right as whatever comes. And so we had then two protections: one artificial island, which keeps the ship running on away, and in addition, two big dolphins. The next bridge which came up and which we did with Greiner Engineering was the Houston Ship Channel crossing. It's now Gene Hartman Bridge called, but we stick with a Houston Ship Channel crossing. And first of all, until now, Houston is, you see here, oil tankers and so on. There's a lot of oil going on. There was a tunnel underneath, but that was too shallow, and it was decided to build a bridge. And one of the main problems was the wide bridge of the bridge. We had, in every direction of travel, 4 directional lanes plus 2 full shoulders on each side, which made it nearly 60 meters wide. And we started, first had 2 cable planes, and found out that it was a composite design, that we found out that in this case we had the longitudinal steel the same amount as the transverse steel. Normally the transverse steel should be only 1/2. Well, each cross girder was 60 meter wide bridge. And so we said, okay, we'll make it 2 separate bridges. And the tower design was relatively clear, 8 towers above deck, but underneath was not clear, and it took us some time to think until we came up with A's underneath also. And now we have the advantage that wind horizontally against the top from the cables and so on is now taken in as a truss in tension and compression down to the foundation, and no bending. So another consideration was that the concrete alternate was given to Jean Muller. And you may remember we had lost the Sunshine Skyway against Jean Muller, and at that time I had 2 engineers with me in Tampa, Florida with Greiner. And I told them, whatever it takes, this time we win. And so we had skinned it really out. The towers have a width in this direction of 7 feet, meaning 2.1 meter, which for a 150 meter high tower is pretty little. And we had a constant wall thickness of 1 foot, 30.5 centimeters, with 4 layers of reinforcement. But we won. Well, that was the name of the game. This bridge lies at the, if you think about the map, it's lying at the Gulf of Mexico. And every year, we just heard it the other day, there are hurricanes running in that direction from the sea over the islands into the the Gulf of Mexico and into the country. And so the governing condition was that we are aerodynamically safe against hurricane. And hurricane has speeds of up to 230, 240 kilometers per hour, which is something. And so it was quite investigated, theoretically, and wind tunnel tests, section models, and it came out the bridge is stable if we stay the bridge down after 4 or 5 elements in the beginning. And so down to the foundations and here down to piles, the bridge was tied down. And in actual fact, we had at least one very bad hurricane going over it. The movement of the two beams, the independent movement, was what had been calculated before, 1.5 meters, something like that, and nothing happened. The bridge was stable during a vulnerable construction period when just the middle part was not closed. That's where the bridge is most vulnerable, and it worked. And since then, I would say dozens of hurricanes went over the bridge. Now that the bridge is completed, it's not so difficult and it stands. You see here, we had during it was quite some discussion of the color of the stay cables. Now the PE pipes in which the parallel strands or parallel wires are in cannot be painted. It's chemically inert. Paint doesn't stick to it. So they are wrapped with bandage. And it's always a big discussion, what color shall the stay cables have? And naturally then the Texas Highway Administration said, we want to have a word. And it was finally said, we make it yellow. Well, that's what it is. And during night, it looks like this. Another bridge in the US was a Broad Street Bridge in Columbus, Ohio. There the problem was that the existing bridge, which had to be replaced, was an arch bridge. But a new arch bridge would have been too expensive. So Leonhard came up and said, we have formerly made so-called plate arches, which are not real arches, but very deeply horned girders, as it is here, and it worked all right. The Annapolis Bridge across the Severn River has the historic Annapolis Marine Academy in the background. And because of that specific surroundings, it was attended as a competition, which is not usual in Germany. Preliminary designs are made and so on. But this was one of the first competitions. And we said, well, everything above deck will compete with the Naval Academy here and so on. So we had a very slender, small, in a way, subdued is the right word, subdued bridge, and we won. Now, then I had now spent about 20 years in the United States, working for Leonhard, but doing design in the United States. I was part of the design team in the US. I was better known there than in Germany. But then it was back to Europe, and the first design task was to build the Helgeland Bridge in Norway at the 30 kilometers away from the polar circle. Now, one may think, oh, polar circle, that's cold. No, it's not. It has some minus degrees, but not extreme, because the Gulf Stream goes close by that fjord, and it's not so utterly cold, but every winter there are very, very heavy winter storms. Every winter storms come in from the left, from the west, in country, and these winter storms have wind speeds of 250 kilometers, which is more probably than a hurricane. And in addition, there were some mountains to the left in the way where we had very heavy turbulence. So 250 kilometers per hour wind with a turbulence of 25%, which is virtually unknown. I don't know another bridge which has such difficult wind conditions. And the storms came. This was here at the beginning of this is free cantilever construction. And we have here pier. And we then said, okay, we want the bridge, that means the beam, to have as little resistance against the wind as possible. And so we said, okay, we'll make it. We tried different things, but in the end, we made it cast in place, concrete, 1.2 meters deep. And there's not much traffic in close to the polar circle, 12 meters wide, which means it has a slenderness of vertical 1 in 354, which is something, and horizontally 1 in 35, which aerodynamically is also very bad. And we had then very intricate calculations. We had our Dr. Kovac, who did all these aerodynamic calculations, and he was proved right, because again, shortly before closure, when the bridge is vulnerable, one of the heaviest storms went over it, and it stood. So quite happy. And I would say that this was the boldest bridge, requiring much courage to design and build it. The boldest bridge Leonhard and Andre and myself also have ever designed. A smaller bridge, Leven River in Edinburgh, we did that with Pepti. And it was, the interesting thing was, the contractor used scaffolding all over the length of the bridge, cast the beam, introduced the cables, and then took the scaffolding down. But that was the way he thought it would be the easiest. So these were some of the major bridges I was in charge of the design. Another task of an engineer is check other people's design, being a checking engineer. And for that, you have to be permitted to work in that country. As sub-consultants, we could always have somebody of the main consultant signing the plans, but as checking engineer, I had to take, and I took the registrations in many countries. In the United States, 2 times 8 hours back to back in Florida, later on in Canada, Pienk. In the UK, I was a chartered engineer and also a fellow of the Institution of Civil and Structural Engineers. In China, a member of the Hong Kong. In Australia, I was in Queensland registered. In Malaysia, I had a temporary license for Malaysia. So it took me a long visiting card to put all that, which is usual in Germany, we don't put that on, but in British conditions, you put it on, it takes you quite some time to line that all out. So in the US then, we checked, I was checking engineer. I didn't do it all myself, but basically I was checking engineer for a bridge across the Roosevelt Lake, which was built with auxiliary tiebacks, and the contractor, he could put things together, but when things became difficult, they didn't understand, and American contractors don't have their own design offices. And so we had quite a bit designed the thing ourselves. It wasn't our task, but that's how it turned out. Svinesund Bridge between Sweden and Norway, lifting of the middle part. I was checking engineer. Then the one suspension bridge, the only one I had was the Höga Kusten Bridge in Sweden with, I think, 1,201 meters. So it is quite a important bridge. Of course, the statical sizing wasn't the problem. I mean, one knows how to do that, how to thick the cables have to be. But the aerodynamics of a suspension bridge are more critical than the aerodynamics of a cable-stayed bridge, because a cable-stayed bridge is stiffer, and the aerodynamics, the wind can take part in that. So it was quite important. Our Dr. Kovac did there quite a bit, and it all worked out. Then came the checking of the Yangpu Bridge in Hong Kong. Now, that was designed and built by Chinese engineers. But they wanted a World Bank loan, I think $100 million or something. And so the World Bank says, yes, you can, we will consider it, but we want to check it. And so there were 3 checking engineers announced, Walt Podolny from the US, who was instrumental in building Pesco-Kennewick Bridge, and Osaka, I think was his name, from Japan, and myself. And so we had various trips, be it to the US, where part of it, the geology was, as to trips to Hong Kong. And I was when the checking was done, I was interviewed by Chinese TV and asked how it went and so on. And I said, well, it went very well. We had no problems. But I say that in a German proverb with a laughing and a crying eye. I say that with a laughing eye because as a checking engineer, you like to say, to hook it, say beautiful and not make problems. But the crying eye was that I said, I see already the Chinese can do it all themselves, they do not need us, and we'll never have a job on a major cable stayed bridge in China. And so it was. But I was happy insofar, you know, my book, Cable Stayed Bridges, and there was a German one. And last year, I had the volume. It is translated into Chinese, which is quite a compliment, because in China, they have more cable stayed bridges than in any other single country in the world. That they still consider it worthwhile, and I mean, that's not somebody in his back room does it, to translate that into Chinese. I thought, well, that's quite a compliment. Checking Uddevalla Bridge, also ship collision was a problem, Ume 11 also. The Penang Bridge in Malaysia was an old German design by Dükerhoff and Wittmann. And that bridge was to be checked for the loadings from various countries, HTO, BS, and so on. And we got the checking job, and we checked that, and we found that, say, the bridge hangs in cables only, and there is no bearing at this point. Can be done, but shrinkage and creep took over, and it settled down there. And we said, well, and then we introduced higher up bearings. That was a change. Otherwise, the bridge was okay. Golden Ears Bridge, Vancouver in Canada, has a special feature that the piers going down here rest on gravel. It's like the Rion-Antirion Bridge in Greece, rest on gravel. So if an earthquake really comes, it can slide on the gravel. That is, and not so much in the, has not to take so much in the bridge itself. I was also working on codes, mainly, as you can see, in the United States. There I was hands-on engineered. I've never done much in Germany. I was mainly in the first in the United States, 20 years, and then 20 years in the rest of the world. So I made the first PTI recommendations for stay cables, which is still valid. It's redone sometime. And then after I had proposed and was used this curve for bridge collision, I was in the guide specifications for vessel collisions in Federal Highway Administration, and finally there was no box girder code in the United States. And then finally they said, okay, we must get around and segmental concrete and so on. And so I was, as a German engineer, asked to serve in that committee also. Now, ongoing projects is mainly, as I said, up to 10 years ago, because since then, since I was retired and my colleagues, which I had introduced, took over, but the Beška Bridge in Serbia at that time was in the end stadium. The Sava Bridge in Serbia is different or special insofar that you have central cable support, but about 50-meter wide beam, and between the cables runs a railway line. So it's a special bridge, and some special features had to be solved. And in India, by the way, I was early on in the early 70s when I was working on the Flehe Bridge. My company did the Hooghly River Bridge, first cable-stayed bridge you all know. And at the end of during Flehe, I was considered to go to India as resident engineer for this Hooghly River Bridge, but it so happened PESCO was more urgent, and I went to the United States and never came back. So I was involved once with a little bit with the Indian Bridge, and then we had 10 years ago the railway bridge across the Chenab River. I think meanwhile it has been completed. There were some hold-ups, but that's the design we made. And Vladivostok, east of Russia, very east of Russia, close to Korea, wanted to build a bridge across the Golden Horn, which is sort of a fjord going deep into the city, and a lot of detours had to be made, and that was very reasonable. And we were helping Most, a Russian engineering office, in the design, and also we were later checking, I think we were checking the towers. This is now since some time open. Then came the idea of crossing the Baltic Sea and the so-called migrating birds line, which is about 21 kilometers, as shown here in this slide. And we had, together with COE, a design with 3 cable-stayed spans of 740 meters, 1 left and right for each direction, and 1 to give it a little bit space between the ships. But it has been decided that it will be a tunnel, a sunken tunnel, which is under construction now. So that's one of the many designs. Then came the Forth Bridge, where we did all the construction engineering for the contractor, which is also completed since, what, 2 years? And finally, the Ruski Bridge near Vladivostok. I was curiously involved in that bridge that we received a telex, or a fax actually, asking whether we would assist in the preliminary design of that bridge. And I said, well, why not? And okay, we'll do it. And after 2 days, they made it urgent. I flew to Omsk in Siberia. You go to Moscow, and then another 3 hours, I think, until Omsk. Vladivostok is another 7 hours from Moscow, so it's quite. Anyway, we had 2 days discussion. It was mainly aerodynamic stability of this world record span, 1104 meters. Before it was 1188, Japanese bridge, and this was 1104 meters, so quite something. It was not really required because the island there, Ruski Island, there's not much doing, but there was a big Asian trade fair or something like that. And for that, the Russians wanted to show, well, we are in the top of things, and it was built, but it's not very much used, to the best of my knowledge. But my involvement was there, and the Russians were amazed what they told me. We've never had somebody come on such a short notice to us. Normally they say it takes 2 months, negotiations and so on. And I said, well, I was running the company, and so I decided we'll go, and the money will come somehow. The money came all right. That was more impressive for them than the technical things I could tell them. Well, final developments, there are many things to be considered. Some, I can take that out. The aerodynamic stability will be an issue the wider, the longer the main spans become. I think with steel and concrete, as we have it today, we can go much further, but the aerodynamic stability is a problem. And so for the damping for the cables is important, and it can be done by changing the magnetic field in which a cable acts. That helps. There can be flaps going up and down, stabilizing a bridge. And when I came to Leonhard I came in 72, maybe 73 or so it was. There was a design, or we made a design for that time for the crossing of the Messina Bridge. At that time, it was still in discussion, and there was certain bridges, and Leonhard said, I will make a cable-stayed bridge design. And we made a preliminary design for a main span of 1,800 meters. And we had no serious problems at all. So I'm not saying the sky is the limit, but it can go very much further than the 1,104 meters we have now. It's not so much a question of how can it be done. It's a question that it is required, and that the money is there by toll or whatever to pay for the bridge. But technically we can start tomorrow to build a 2,000 meter span. Well, thank you very much for your kind attention.
Thank you, Professor. It was an amazing talk that you gave us, something that really inspires us to excel as bridge engineers. The difficulties you faced and the problems that you overcome are lessons for us all to learn. And your contribution to this field, be it in ship impact, be it in the various forms of aerodynamic damping and control, be it in contributions to codes worldwide, show you as a truly global citizen. Your contributions are to engineers at large all over the world, and we absolutely salute you for this. Alok, may I call upon you to add your comments and views and words, and thank Professor for being with us. A formal vote of thanks.
Thank you very much for your kind words.
Thank you, Harsha, and it was indeed an amazing lecture from Professor, and I think we were truly, amazed by this. And I think this is just an unbelievable way to begin this lecture course. Most importantly, I must profusely thank Professor Holger Svensson to have readily agreed to allow us to show his all the lecture series to the participants. And when I wrote to him, I was not quite sure whether I will be given the permission, but I was really pleasantly surprised to receive his return email within a day. And that was really amazing. Then we discussed within ourselves that whether, the publisher will have an objection because it's a part of the book. So after 2-3 days, I again hesitantly wrote to him that, look, you have given permission, all right, but whether we need to take permission from the publisher. And within 24 hours, he wrote back to me saying that, I have the, you don't need to take permission from the publisher, and I am having the rights. So, I just, I don't have words to thank Professor Holger Svensson for giving us this opportunity and for disseminating the knowledge. The reason why Indian Association of Structural Engineers exists is the whole objective is not to earn money, but to disseminate knowledge, to build capacity of the structural engineers. And I thank you because you have been a part of now this, exercise. Thank you very much. And I would request the moderator, Dr. Subbarao, now to open it for the panel and for the question answer.
Thank you for your kind words.
Sir, we will take a few questions, Professor, from the audience after the panelists give their views and comments and add to this fora. So may I first call upon our doyen and our foremost bridge engineer of the country, Professor Mahesh Tandon, to share some of his views. Professor Tandon, can you start with sharing of your views, sir?
Thank you, Harsha, and what can I say? I'm absolutely dumbfounded looking at this presentation. I can only say to Professor Svensson that we have traveled with you, along with you. It was as if we were a part of a safari. First, when you went to South Africa, and in your safari suit, it seemed that we were also camping there. How realistic that was. Then I think we enjoyed your 20 years in the US and some of the, I think the most important bridges that you were showing, really they are still landmark bridges in the US. For example, the Sunshine Skyway Bridge, which of course you said that you lost, but then you got many more. That was the first choice.
You can't win them all.
But this East Huntington Bridge, the Houston Tunnel, and of course your Swedish bridge about the Helgeland Bridge. I mean, these are some things which has such a narrow deck. I think it was some some L by 350, if I remember correctly. That is the depth of the bridge.
Yeah.
That was the depth. And having a span by 35 as the deck width, I think all these are the least one can say is that they are aerodynamically a big challenge.
Yes.
And you did show us a few things about how you got over them, but I think that it's absolutely amazing to see this and be a part of the journey that you have taken us, not only of cable stayed bridges, but your professional life, which is going to be an inspiration for all the youngsters who are participating in this online lecture series. And I'm sure many of them will have questions. I have a question, but I think that I will somehow hold that, resist to ask that question till other people have had a chance. So thank you very much, Professor Holger Svensson.
Thank you for your kind words.
Thank you, Professor Mahesh Tandon. That's very interesting comments of yours and very true all what you said. May I call upon our own Sharan Saab, Mr. Sharan, to speak a few words, his comments, his thoughts, and his messages to us.
And foremost, I must congratulate Professor. His last few lines were so important and so amazing to me. He was so moderate when he says that the bridge he has shown, this is length main span 1.8 kilometer. And he was so moderate, he was so much humble that he said, don't think the sky is limit, but I'm sure that what he said, there much more than 1.8 kilometer bridges must be in his mind. And I'm sure that he must be looking in due course of time to come. So that was really an eye-opener to me, in spite of, apart from his taking over entire world and showing the bridges in most part of the world. So that is what is very much encouraging, and he has really given us glimpses of his work done in the past, and we are very much thankful to him. One or two things which definitely I would like to point out here. When I was young engineer in the ministry, when this in Calcutta, the cable bridge was under construction, second Hooghly Bridge. So we thought that it will come in a very shortest possible time, but to our utter surprise, it has Mr. Tandon always knows that this has more than 9-10 years for commission. So that was only the drawback when it started. Otherwise, by now time, India must have had many more cable stretch bridges apart from this Nani and Chambal and Bandra Worli ceilings. So when we started, our construction took long time. So we thought that this type of technology is time consuming and may not be, we are not fit at that very time to carry forward. So that was one of the things which really I want to understand from Professor. What is the minimum time with the latest material technology and advancement, because he has mentioned about the cable technology of strand and PTI and etc. and other things. So is there any possibility what the speed has become the one of the things? When I was in Japan, I've seen alignment was not fixed, but many cable stretch bridges was coming in the rivers. So I was asking, where is the road? He said, don't worry, we will make the road later. Let us first construct the cable stretch bridges. So there are a number of bridges. When I visited Osaka, then Kobe, and I was utter surprised. What type of technology they are doing? They are first building the bridges and then leaving the road alignment to be constructed later days. So that was eye opener. Apart from whatever I could understand and learn today, it was a knowledge which is really important. One last point which I just wanted to before, because we are developing with Mr. Professor Mahesh Tandon in P9 committee the our guideline for cable stretcher bridges, where we are restricting for concrete bridge up to 350 meter, if I remember so, and for steel and concrete composite 500 meters. So with today understanding and knowing from professors, we will also like to add on and what else can be done, but we are in a very much hurry because as on date we don't have any document in India where we can go for guidelines. So we'll make an beginning, and whatever we are understanding from professor today, we will definitely like to add on when the time keeps coming. That is what I have to tell at this moment. Thank you.
Thank you. You could use my, if you don't have anything, you could use my book as a guideline. Most points which are important for the design are in my book. I don't think you have to take that as an Indian code. But
Thank you very much.
Thank you, sir. Thank you, Sharan Saab, for those comments and those observations. Yes, we are in the IRC in the almost completion stages, hopefully within the next few months, of bringing out a guideline for the design of cable-stayed bridges. We will, with your permission and with your kind, graceful permission, take parts from your book which are most useful for the development of that code. So I thank you for that a priori.
You are most welcome.
Thank you, sir. Thank you, sir. And may I now call upon Mr. Vipul Ahuja to say a few words and on whatever topic, whatever issue. Vipul, as the convener of the whole committee which puts together the events for IAStructE, may I call upon you to say a few words.
Thank you, Harsha, and I would like to profusely thank the professor, for his amazing journey through of his life. As a structural engineer and as a professor, a teacher, a mentor, even today, towards when people are thinking of, retiring officially, though you retired, you're really not retired. You have.
I think we have lost his
Vipul,
connection.
we seem to be losing your connection, Vipul. I'll go ahead to Pandey Sahab. Pandey Sahab, welcome. We are very happy to have you here on this event. We've had a wonderful exposure from Professor Svensson on cable stayed bridges. Vipul, I've just moved on to Pandey Sahab. I will come back to you. And
okay, I think my this thing was, but anyway, but I really thank all the panelists also for being present here, and I hope we will have a very fruitful discussion, and the audience will get a chance to learn and to interact with the professor as well as the other panelists, and draw upon this very important experience. And we are, as a nation, very ready for taking off on our very important infrastructure of bridges, especially. And we need that capacity building today that has been around in the developed world. But I'm sure that we will catch up pretty soon. Thank you so much for being here with us and gracing this occasion. And we look forward to the rest of the lecture series, which is going to be so enriching for all our audience. Thank you so much.
Thanks, Vipul. Pandey Sahab, welcome. May I request you to say a few words, and especially where we are in India and what your plan is in the development with cable stay bridges and extra DOS bridges and the like, sir. Thank you very much for being with us today from your difficult times and the times that you're in and the pressure that's on you. We thank you for being with us.
Good evening, everybody. Good evening, Professor Svensson. I'm really delighted, and it gives me immense pleasure that I could understand that there is some text or some book from the experienced people like you, where I can depend upon for any guidance, because India has already ventured on a very ambitious program of infrastructure development. And at the moment, we have planned around 6 or 7 bridges, which are cable stayed or extra rod bridges. For your information, I would like just to inform that we are already constructing a cable stayed bridge of 500 meter span at Great Dwarka. Another 3 bridges in Bihar are planned. One is around 5,000 meter long, having 22 span of 220 meter extra rod bridges, and having a 4 continuous spans in that as well. Then we have a Fafanau bridge at Ganga in Allahabad, where also we have an extra rod bridge of 300 meter span. Another 2 bridges are coming up in Kosi in Bihar again, and Vikramshila Setu. I would like to just have a view from your side, or I'll go through your book. There we have a special design challenges, that one span is 72 meter, another is 109 meter, just side of it, and another side of it is 142 meter span. I don't know how it will be designed and how intricate the design will be. So I'm really thankful to the professor, where I could get some insight into the design aspect of the cable stayed bridges, especially the very intricate designs, and certainly we will get a lot of benefit from your lecture and certainly from your book. Thank you very much. I'm in Institute of Engineers, Bridge Engineers as well. I thank them all to give me an opportunity to attend this talk and have some benefit from the professor's talk. Thank you. Thank you all.
Thank
you, sir. Go ahead, Professor. Professor,
No,
please
I just
respond.
wanted to thank.
Yeah.
That's all.
Thank you. Right. Friends, we have had our views from our panel. I could take a few questions from the audience if that's okay. I will start in reverse order because probably that's the questions which people have had for some time and thinking. I'll go back in reverse. What are the suggested ratios of span to depth and width to span that work for spans greater than 1,000 meters with concrete and also with steel composite concrete in preliminary design, based on your experience? That is span to depth and width to span for 1,000 meter, 1 kilometer bridge in concrete as well as in steel composite.
Well, width to span is normally not ad libitum because the road, the traffic situation requires a certain width. And with that, you normally have to live. You can't say this span, this width. That's normally a given. And now the depth, as I said, we have 354 with Helgeland. Professor Schleich has a bridge in Greece with 1 to 420 or something, even more shallow. It is a question of the whole structure together. We at Leonhard and Andre, Professor Leonhard himself, tend to have the width, the depth of a bridge as small as possible, have a shallow bridge. And it is, one can't really say, I wouldn't go beyond, say, 350 or so, but it has to do with the interplay of the forces in cables, towers, backstays, and so on. One has to calculate that really, and of course the bending moment, it's a question of the life loads.
Yes.
If you have really heavy life loads, you can't go so shallow as you can go with lighter life loads. H2, for example, is a lighter life load, not so heavy a truck. I can only show the examples I have done, but not say this is it, or thou shalt use this or that width.
Right. Right. I take it, that was from Saravana Sonai, the person who asked the question. Now, Ranjit Ramnath has a question. Is it mandatory to have a wind tunnel for all cable stayed bridges? Can the wind parameters be codified?
Well, that's a good question. Codified, I would say no. For the special bridges, they are always special. But for wind tunnel, I have a conviction that for the section model, as we call it, where you just have the cross section, some 2-3 meter wide, and let the wind go over, and take from those the aerodynamic parameters. That is good. And you should then use these from a section model parameters as input for the computer calculation of the whole bridge. Now, I'm not in favor of wind tunnel tests of total bridges because the dimensions you can model of the deck or so are so small, they are more or less meaningless.
Yes.
Very often, government people who don't understand the aerodynamic considerations, they say, well, let's make a model, and if that is strong, then nobody can tell us we've done something wrong. Yes, that is normally the reason, but in true life, I would go for a section model, just a cross section in the wind tunnel, take the results and use them as input parameters in the computer calculations.
Thank you, sir. I think that has been understood by all. Very clear answer there from Professor. One very broad question that's being asked is, kindly let us know the process of awarding the contract for building a bridge in Germany. What's the contract award process? In India, we go mostly by the lowest bidder. Is it the same in Germany or maybe America, your world experience?
Just, it's different in every country.
Right.
And I can tell you in Germany, first of all, the design is tendered. So consultants line up and say, I want to design this bridge. And it can be in up to, we have our certain code for this, which shows up to 6 points from preliminary design to detailed design. And I would say that normally, on one hand, the lowest bidder is awarded the job. But either you have a pre-qualification or you have to qualify your proposal with, roughly speaking, examples you have done.
You're right.
And now the designs are always given to consultant's office. A contractor today, 100 years ago it was different. A contractor is not given a preliminary design.
Right.
Now, if the preliminary design is given up to, say, phase 3 or 4, then comes the detailed design. Now, the detailed design can either be done by a contractor. A contractor has its own design office in Germany. Not so in the US, or it can be a consultant. And in addition, you have a checking engineer who is chosen by the government.
Yeah.
It is an involved process. But basically, it has to do with experience and price.
Thank you, sir. There, Professor, I will take a few questions because it's very rare to have someone of your eminence and your experience with us. So the audience, there's so many questions that I could probably take a few more if you'll allow us. So there's a question from Venkat Lute. Sir, is there a permissible deflection limit? Is there a permissible deflection limit for the main span? And under what condition are those limits to be sort of imposed?
Yes.
Oh dear.
Leonhard always fought that idea of permissible deflections. It's not the deflection itself, if you have a long span. It is the inclination you reach by the deflection. If it's a long bridge, you may have the double deflection and the same angle. There is no, say, on a continuous girder, there are limits. I mean, that's fixed and up and down. But for a cable-stayed bridge, there are no deflections. It depends on, say, the inclination and so on.
Thank you, sir. Thank you. Are there certain environments in which cable-stayed bridges may not be adopted? Is there any situation in which we simply must not use a cable-stayed bridge?
I would not say that. I mean, heat, wind is there. If it is a cold climate, one has to give special considerations of ice falling from the cables or from the tower, but that can be solved. No, I would not say an earthquake even. I mean, if we have heavy earthquake, there are new technologies like Rio Antigon in Greece, where the whole bridge can slide up to 2 meters on gravel. there are always solutions for any environment. I'm so bold to say that.
Right, sir. There are so many questions. I'm just going to randomly choose a few because I might send them to you and you could reply and we could add it to our website, because some questions, there are many, and I could take a few now. If you will very gratefully reply those in short, I could post them on our institution's website.
Yes, please do.
So all attendees could have it. Right. The other questions, let me just see. It's like playing poker, you know, you have to pull a card out of somewhere. So, yes, how was the Wittingen Viaduct built? How was it constructed? Because the user deck support arrangement, how was it built actually? This is from Sony, GSD Sony.
Sorry, I didn't understand. Which viaduct?
Wittingen or Weilingen?
Wittingen. Okay, Wittingen.
Wittingen Viaduct.
Wittingen, yes.
Could you speak about how it was actually constructed?
Yeah, it was constructed in free cantilever. So there was there were auxiliary supports where the air strut was later, and then half span-wise and so on, it was built in free cantilever.
So the auxiliary supports were how tall? From the valley floor up?
120 meters high.
Right. That's probably the question he asked, which is a very, very pertinent question.
Yes, and it was difficult, at least for checking. We did then the checking on that, because Krupp, who did it, the German contractor Krupp,
right.
He had to use auxiliary piers, which were from old times, and the steel wasn't so clear, and the steel had to be checked to make that acceptable. So there was quite a job with these 120-meter high piers, because they are not readily available. So
Right.
old, say, steel used, and it had checked, but it worked all out.
So there's a question from, thank you, sir. There's a question from Pratik Devkar. Sir, you have mentioned that in composite deck alternatives, the creep transfers the post-tensioning compressive force to the steel where it is detrimental. Can you elaborate more on this and how it can be overcome in composite deck, the creep?
Well, we have the concrete slab, I say, on top, on the steel grid at the bottom. If we need post-tensioning, we need it in the roadway slab. So the roadway slab is post-tensioned. And so for at T equals 0 at the beginning, you have a certain compression stress in the slab, which is bigger than the tension which comes out of life load, and no compression in the, nearly no compression in the steel underneath. But due to the creeping of concrete, the concrete shies away, so to say. The steel is, the force runs into the steel. And so the compression stress in the roadway becomes less because it's creeping away. And in the steel, it becomes more because that creeping away makes it to be in the steel. And so that's detrimental. I mean, you don't have all the post-tensioning still there you had in the beginning, and you have some compression in the steel, which you have to take into account. Now, what to do against that? That is true in general for all cable-stayed bridges. Now, going back to one step. A cable-stayed bridge is under compression. Compression goes up maximum at the towers from the inclined cables. But there is no compression in the center, because there's the cable there, there's the cable there. at a very short distance of the center, the
Yeah.
compression from the cables is normally big enough to overcome any tension from life loads. Tension from life load means you have a negative moment with life load standing left and right, and it
Yes.
bends through. Okay. And you want to avoid the post-tensioning. So what you can do is that you put a moment in the center part. That means the shop form is such that the shop form has a hogging moment, and then when you have it straight, you introduce a negative bending moment from shop form. Under permanent loads, that also creeps a bit away, but it's not so important. You can just add that. And you need it only for a limited period, 2-3 cable distances
Yes.
in the center. So you, instead of post-tensioning the deck, you put compression into the deck acting as a top flange.
Yes. So you intentionally pre-compress the deck. You
Yeah.
intentionally put in additional compression in the deck to counter this effect. Right?
Exactly.
Right.
That has been done. It's not required in concrete. Concrete, I mean, there the whole cross-section creeps. That
Correct. It's uniform. Yeah.
clear, but it's only in composite bridges that have normally introduced a negative moment in the center.
Yes. Yes. Now we have a question. Thank you, sir. We have a question from Vian Hegede, one of the IBAC's foremost members and a member, a lot to do with bridges in India. He had been with Gammon India before, and now he's the CEO of IAStructE Consultants. It's a pleasure to have him with us. Professor, it was a pleasure hearing from you. For cable stayed bridges, whether you personally prefer steel composite superstructure or all concrete superstructure, what's your personal preference?
It depends. Normally, you can say the following. Up to 400 meters, roughly, concrete is most economic. 400 to 600, 700 meters, composite is most economic. Above that, steel is economic. And then there is the mixed form, where you have a main span in steel and a side span in concrete. The side span then acts as a cantiledge to the main steel, to the main span.
Right. I'm just looking for questions that would add to the. Again, from Hegde, another question, which is there any guidance for load testing of cable stayed bridges anywhere in the world? And on that same point, I would like to talk about a question which has been plaguing all of us in India. Is we have a limit of 200 meters or so for considering live load, the loaded length, as it were, in the European equivalent of the loaded live load length. But we have our class of loadings that we have in India for normal bridges up to about 200 meters. Beyond that, the behavior and the response are coupled, and the live load, would the same representative live loads be acceptable? Vehicular live loads that we use for the design of our normal bridges, would they be acceptable when spans become very large? Do we need to do special assessments or consider different forms of loading or combinations of loading or types of loading?
Could you just repeat the beginning?
Yes.
You said,
load testing. The point was about load testing.
Okay. Yeah. Load testing, I'm not aware that there is a code, but I have been personally present or heard about others that you collect the heaviest live load available. I remember one Rhine bridge which we designed. We had US tanks going one after another over the some lengths, and otherwise you use trucks with heavy loads and so on. So I just want to point out, it's not to check whether the bridge falls down. We know the bridge doesn't fall down. It is there to check, for example, whether the stresses are all in the order one has to calculate, but it's not the risk of falling down.
Right, right.
Now, life loads for long bridges is a difficult example. On one hand, these heavy life loads you normally have for shorter ones are only, so it may be right to use a staggered arrangement of loads, that the heavy loads you have for the normal bridges are only for some 200 meters, 300, and then you have a lighter load. But I don't think there is anything, I have been in discussions on bridges like that. But I'm not saying I can make that a general point. That has really to be decided on the bridge in question.
Right. Thank you. We are grappling with that in our committee because we thought whether the normal representative loadings that we have would be adequate because of the different type of response this structure has with the longer span.
I know it has to be, I mean, if you have to load, say for negative moments, 2 shorter spans, is that load reasonable? Or for, if you have to load the side span together with the main span, shouldn't be there a factor to take the further away load down? I know it all, but I don't have a ready answer for that. That has to be discussed in every single case.
You're right, right. Oh, this is a question from Mr. Suhas Kedkar, again, a person who's been involved a lot with bridge construction, cable stay bridges in India too. The Houston Ship Channel cable stay bridge has twin A-shaped pylons. The pylons are very slender in the long direction. The Bandra-Worli Sea Link in India has similar twin pylon, but it also has an A shape in the longitudinal direction, which makes it a diamond shape. It's a diamond shaped pylon. It's a space truss and a much larger longitudinal stiffness. Since I was involved in the Bandra-Worli Sea Link construction, I'm interested in knowing your views on the longitudinal stiffness of the pylon.
Yes, I'm not sure I get what he wants, but I can give one example, which is puzzling in the first, when you hear it. When you have vertical tower legs, you have a certain torsional frequency of the beam. And when the beam is in torsion, the tower legs go back and forth. Now, if you put the vertical legs in an A shape together, then they cannot act independently. And thereby, by choosing an A tower, you increase the very, very important torsional frequency. So that may give an example, not so obvious, on the stiffness of the towers. I'm not sure I have answered it completely.
Yes, in a way, the benefit of using such a shape to increase the torsional rigidity, and of course the benefits to wind and also structurally the stiffness augmentation. That's probably the point that you're making is very valid, and I think that should be the answer for the question.
Okay, fine.
The other point being asked is by a gentleman called Ashish Srivastava, also a bridge designer in India of repute. Even in Norway, where wind speed is more than 250 kilometers per hour, was it advisable to go for a cable stay bridge in that condition?
Well, that's a good question. There were people, engineers, who said that bridge will fall down during construction. So one could have said that's not the right way and you have to do something else. As I say, it was our boldest bridge. We were courageous enough to try it, found out during the design that we can calculate the stresses, and it worked. Somebody who is more feasible says, no, we can't do it. It's a question, as I say, of personal boldness. I'm not sure I would do it again. I'm not sure. I was quite a bit younger at that time, but we had a good team and we calculated it and we believed in it and it worked. Some other says, I can't believe in that.
Let me ask you some more questions. Thank you. Gaurav Ghai, asking this question, a very young engineer, very hardworking and an enterprising lad. So his question, I think, deserves some answer from you. What about using alternate materials instead of concrete, like some form of plastic or to paraphrase CFRP and the use of Kevlar and where we're going today with the new materials which are more sustainable, which are more, whose physics and chemistry is being better understood and their design process are being better addressed. Is there do you see some future in a non-concrete, non-steel composite, but in a completely, say, plastic material of some sort?
Yeah, that's quite a question which is often asked. And we even have in our company, Dr. Andre, the son of the founder, he is investigating from Kevlar to plastic strengthening of concrete bridges and so. So we are involved, but we are aware of the possibilities.
Right. So as such,
but when it comes down to if it comes down, it is always or has been always quite a bit more expensive to use these new materials, although they may hold longer and so on. But money talks. It's a fact in engineering. Well, it's no use discussing. I mean, that is, and if it's less, I'm not saying cheap, but less expensive, I like to say, more economic, then we go to the old materials. It's a question once the new ones are as good and cheaper, they will be used.
And their costs are coming down as time goes by. So somewhere in the future, we may look to such structures, but not at the current time.
By all means, especially for the long spans. I mean, you have less sag if you have a Kevlar cable. We know all that, but until today, it's not feasible. It's not economic.
There's a question from Dr. Harshad Birajdar. Are there limits for minimum and maximum angle of cables? Are there limits, maybe by fatigue criteria or any other criteria?
I know what you mean. If you have too flat an angle, the cable force becomes too big. And if it's vertical, let me put it this way, for a harp arrangement in parallel, you have a steeper angle, then you have for a what did we say? No.
Maximum minimum angle of cables, yeah.
Yeah. It's, if you want a figure, a minimum, I mean, it's, you can't, but the minimum is about 20%, and the maximum naturally goes down to the tower. But if you try to calculate the required depth or height of a tower,
yes,
you come from very steep to vertical, and the optimum lies for a tower with 20 to 25% height of the main span.
right.
And from that, you can calculate the corresponding angle. And all I say is for a harp, they are all the same.
All parallel.
You need a little bit more than for another arrangement where they go from 0. So it's not a question of trying to find the optimum. If you go to by the tower height, you find the tower height is that, and that's it.
Right.
It's, by the way, all in my book. There are
because the audience are so involved and so eager to learn and hear your voice say it, from your voice, you know, the guru. So
okay.
I'm allowing some more. Alok, do we have time to take some more questions and have the...
I'm happy to answer that.
There you go. Do we have time to extend, you think? We should go ahead, Alok?
Yeah, not too long. I'm getting...
Okay, say another 10.
I think another 2-3 questions you can take up,
okay.
and then we can...
the rest we'll answer later.
Rest we will answer
Thank
later.
you, Professor. Thank you. Sachin Oak, who used to head a bridge division of a company in India and is now an independent consultant. Sir, with current advances in technology of BRIM, that is bridge management systems, where do you think we young engineers looking to, or is the future development, or is the future development in cable stayed bridges? You know, with this move to BRIM and all this, is there any, the larger question is the importance of, say, conceptual thinking and the importance of non-computerized independence of the engineer's frame of mind and his individuality being expressed. Are those being swallowed away or taken into the BRIM paradigm today? I'm paraphrasing questions as I'm taking it from the audience too.
I can't talk about the BRIM in detail, but you need both. You need a concept which is completely independent of any computer calculations or concept. Even I go as far and say a preliminary design you can do by hand. And I've shown that in my book, and that can all be done. And my students have to do it. They all have to design a cable stayed bridge in their. On the other hand, you cannot finally do it without a computer. Both are possible. I myself, I'm not very capable of handling a computer, but I can check the results and say that's right or that's wrong. But basically, I'm in the range since many years of preliminary design, and then, but finally necessary, it has all to be confirmed by computer calcs.
Thank you, sir. So another question from Mr. Vinay Gupta, who's one of our, most important bridge engineers in this country and works with Professor Mahesh Tandon as his CEO in his company. And he's the head of Indian Institute of Bridge Engineers also. At the moment, he's the president there and the president of the Indian Concrete Institute. His question is, you mentioned that deck width is decided from functional considerations, but certain minimum width becomes essential for lateral stability. Could you elaborate?
Yes, yes, no. Let me give an example. The Helgeland Bridge, which you remember has extremely, has 1:35. Well, there is virtually no traffic at the polar circle where the bridge is located. So all you need is 2 lanes and 1 footpath. There is not more required. And whatever the length is, there is no more traffic. So you have to go by the requirements and then see how to fit the bridge.
Right. So the functionality will decide, the functional requirement will stem from the traffic use and the demand and the lane widths and fix the width, and then you design against the issues that are evolved.
Yeah.
Now, there's a question I'm very happy to note. There's a gentleman called Diego Camara Garcia. I'm very happy to note that. I'm not sure which country he's from, but welcome. Have you been involved in the study of solutions for widening of cable-stayed bridges for addition of lanes?
Yeah.
Obviously coming from, adding width. Do you think that we will start seeing these solutions in the future more often as traffic demands increase?
Yes.
As far as I know, only Rande Viaduct has been done.
What
R-A-N-D-E.
What viaduct?
Rand, R-A-N-D-E. Rand Viaduct, Rande Viaduct.
Where I was, at least my company was involved, was in the widening, oh God, the name, in England. There was a cable-stayed bridge and a lane was added. And so, where was a stay cable added to, so you can't just, it depends always.
Right.
But you can, it has been done that you add a lane plus suspend it with a few cables. It has been done for suspension bridges, I know. So it requires some ingenuity, especially if the cantilevering becomes too large that you have to support it from the top. But it has been done, and I could imagine that it will be more often done. It's just a question that the whole changing of the bridge is not, and what remains and the lifetime is not more than comparatively new bridge would cost.
The question that arises, of course, is that if you have two planes of cables rather than one plane of cables can, if it can be designed, over-designed initially, then maybe we can have lateral augmentation of lanes. But with two planes of cables, that becomes even more difficult. So
in principle, I agree, but still it could be that even with two cable planes, there was a strengthening of the diagonal or so. It is more, it is in principle right. Yes, okay.
Humber Bridge, yeah. Okay, now a question from Vijay Deshpande. Just two questions more, then I will stop.
Yes,
can the measurement of dynamic response? Okay. Can the measurement of dynamic response of the stay bridge be related to load capacity? The load capacity, can we relate dynamic response to load capacity?
I'm not aware. I mean, there may be theoretical investigations, but I mean, what you want to do is you want to excite the bridge, measure its response, and then say it can carry 100 tons.
Yes, that's the question.
I'm not aware. That's reliable.
Okay, the last question. Then I'm sorry, gentlemen, participants in the audience were deeply, we're touched by your response to so many questions. Questions are piling up, so I don't think Professor can take them all. So this is the last question, and the person's name is very interesting. That's why I picked this question, Professor. His name is Mohammad Azharuddin, who is a very great Indian cricket player, by the same namesake. So Mohammad Azharuddin is asking this question: what modification has to be done in the design if we get adverse results in wind tunnel testing of cable stay bridges? What do you do once you don't get good cross-section parameters?
That is a question which takes place quite some time in bridge design. That everything else seems to be fine, but aerodynamics, well, you can, first of all, you can dampen the cables with sort of shock absorbers and so on. Then you can dampen the whole bridge longitudinally at the towers by also some shock absorbers, and you can change, and that is investigated in wind tunnels, you can change the edge configuration. Instead of having it just straight, you can add some sheet metal in an angle and in a length, which can strengthen it quite a bit. And there I have, well, it's also in the book. I mean,
yes.
There is an example for the, I think it's the Cap Shui Mun Bridge in Hong Kong or so.
Yes,
Well, there is a small, apparent small change in the edge configuration.
Yes.
And an amazing increase in critical wind speed. So damping is by calculation. Modification in wind tunnel is in wind tunnel.
I think, Alok, I think we should stop because, Professor, the questions keep piling up. So I don't think it's fair to keep you so locked in. Thoralf, I think you've assisted in a wonderful manner. Thank you, Thoralf, for being there also. You know, it's wonderful to have this smooth flow of everything happening today. Thank you so much. Alok, may I hand over to you to say a few words, and then maybe you speak a word of thanks, and I will speak there, or I will speak now about the future events, and then you can give a formal vote of thanks to all. So
okay, you speak first.
I will just 2 minutes, Professor. It is, as you know, gentlemen, ladies and gentlemen in the audience, Professor has very kindly agreed to us to use 30 lectures of his, which are a 2-semester course at Dresden. This is for the first time that something like this is being allowed or being done in this part of the world. And you might know that amongst your participants are people from various countries in the world. And as Professor said, knowledge is free, and I want it to be shared. And it's his life experience which we are sharing. It's not just simple knowledge. It's wisdom plus knowledge plus highly advanced understanding of this wonderful type of structure, the cable-stayed bridge. So we have now a series of 15 lectures. We have grouped two lectures together, and there will be on Wednesdays and Saturdays, as you know, in the registration pamphlet, there was the times announced, and we shall rigidly stick to it, 4 o'clock to 6:30. Please note that there will be expert panelists for each session. If it's a session on wind engineering for cable-stayed bridges, we will have people from RWDI and from the wind engineering world on the panel. So we will take questions in each session, and mostly we will try and answer them all, either at that time or later. So the idea is, the book by Professor Svensson is a wonder book. I strongly recommend it for everyone to know and read when you get a chance. But the idea is these lectures will bring us all together, all of us who love this kind of a bridge and who want to build these bridges in India and maybe elsewhere in the world, and bring us together to share knowledge using this platform that Professor has provided as a fora to bring us all together. In these COVID times, it's a wonderful contribution from you, Professor, and we thank you again for it. On that note, Alok, I will hand over to you. You must sum up the proceedings and Vipul. Yeah.
Thank you, Dr. Subbarao. I don't have words to express my sincere thanks to Professor Holger Svensson, but let me give you a vote of thanks first to all the participants. We have 300 plus 326 registered participants, though I saw today total participant was about 300. Thanks to all the participants for registering, and I'm sure you will, end of the day, after 15 days of lecture, 30 lectures, you will be enriched. I'm quite sure about it. Second, I would like to thank all the panelists who have spared their valuable time and enriched us with their insights. And lastly, I profusely thank Professor Holger Svensson for sharing his life journey, the stimulating professional journey of his life. And I'm sure that would be quite inspirational and motivating for all the young engineers that we have. And I'm sure a lot of lessons learned by them. I mean, structural engineering is such a beautiful profession. And I think one can go through your journey to understand this. on this special day, as I mentioned in my opening remarks, that today is a special day for us because it's a Teachers' Day, and we could not have been treated better than a teacher like you. And I tell you, you have now 300 plus additional students permanently registered with you, and I end up with only one note: Happy Teachers' Day, sir. Thank you. Thank you, everybody.
Wonderful. Wonderful. Thanks, Alok, for that message from our president, sir. Gentlemen, ladies and gentlemen, the audience, one short announcement. We are accepting registrations till Wednesday. Please note there is an extension in the registration because the formal teaching part will start only from Wednesday. We haven't covered the formal teaching part will start from Wednesday. And if you or your friends in the participants want to invite others to join, please feel free to do so. We will accept registrations till Wednesday latest. So see you on the 9th from my side. I will, as moderator, see you on the 9th, as will many of my other colleagues and specialists and experts in the bridge community at 4 o'clock on Friday coming. Dipl, may I ask you to say something on future events and anything, or bring the event to a close otherwise?
Well, there are, please take heart, other non-bridge engineers also, or people with overlapping professions. Other seminars are coming up on buildings and rehabilitation of buildings, and we're going to take that up in a big way because, you know, a lot of buildings are coming of age and earthquake codes have changed in India. So there's a lot of activity happening in that. So we are planning, you know, some activities in that direction as well. And of course, you already know about in bridges, in I think fatigue of bridges also. There's one seminar which is going to be coming up very shortly in between. So that's also going to be a very interesting event for bridge engineering. So we are trying our, in fact, I would also encourage building engineers to be working, to be listening on the bridges as well, because there are a lot of overlapping technologies, you know, which are there, like Professor just mentioned about damping. That was pretty obvious for building engineers also. You know, that is because in tall buildings also we face a lot of similar problems where we have damping and, you know, one area is after a bridge is also just structured like very tall buildings. So we can extend similar technologies, and we've had you know, very good courses or seminars last year on performance-based design, and I think a lot of those concepts, resilience of bridges, you know, resilience of buildings will be applicable to bridges as well. Like we're talking about probabilities, you know, of collapse. So probability of collapse should be same for wind and seismic. You know, why have different probabilities for different things? So we have a lot of unexplored areas on which we have to talk about. Right. So I hope that everybody will be, you know, keen to learn on this topic and other topics that your association is going to take up in the future. Thank you so much.
Thank you. Wonderful.
So yeah, we close the today's you know, presentation event, and thank you once again, Professor, and thank you all.
Thank you all participants from my side, and I now call you Guru Svensson. Guru Svensson. On that note, sir, thank you for being with us. Thoralf, thank you for being with us too. Righto.
Yeah, thank you, Thoralf.
Let's call it to close.
For your
okay, Vikas, call it to close. Goodbye.